To understand Poisson's ratio, consider a body that has a length L and a square cross-section, with sides of length A. When a body is subjected to an axial tensile load, there is an increase in the length of the body, but at the same time, there is a decrease in other dimensions at right angles to the line of action of the applied load. So the body feels axial deformation and also deformation at right angles to the line of action of the applied load. The ratio of axial deformation to the original length of the body is known as longitudinal strain. The strain at right angles to the direction of applied load is known as lateral strain. The ratio of lateral strain to the longitudinal strain is a constant for a given material, when the material is stressed within the elastic limit. This ratio is called Poisson ratio, and generally denoted by μ. If longitudinal strain is tensile, then the lateral strains will be compressive. If longitudinal strain is compressive, then lateral strains will be tensile. So we can say, lateral strain is equal to, minus μ multiplied by longitudinal strain. For homogeneous isotropic, linear elastic materials, Poisson's ratio can theoretically range from, -1 to 0.5. Most materials have Poisson's ratio values, between 0 to 0.5. For cork Poisson ratio is 0 and for rubber is 0.5. In this table, we can observe that Poisson ratio is greater for ductile metals than for brittle metals. Auxetic materials are those that exhibit a negative Poisson's ratio, meaning they expand sideways when pulled, and contract sideways when pushed. Its use in personal protection, biomedicine and sports equipment. Some auxetic materials are bandage, bulletproof vest, sport shoes, helmets, gloves and pad. Applications of Poisson's effect. Poisson's effect plays an important role in pressurized pipe systems. When a pipe contains a fluid or gas under high pressure, the internal pressure applies an outward, uniform force on the pipe wall, creating hoop stress in the material. As a result of Poisson's effect, this circumferential stress causes the pipe to expand radially, increase in diameter, while simultaneously contracting slightly along its length. Although the axial shortening is small for a single pipe section, it can become significant when many pipe segments are connected in series, since the contraction accumulates. This cumulative shortening can place additional forces on pipe joints. If the joints are restrained, these forces may lead to separation, excessive stress, or even joint failure. Stress and strain relationship for three-dimensional body. A three-dimensional solid is subjected to three mutually perpendicular normal stresses, denoted as sigma-1, sigma-2, and sigma-3, acting along the x, y, and z directions respectively. Consider the strains produced by each stress separately. The stress sigma-1 will produce strain in the direction of x, and also in the directions of y and z. The strain in the direction of x will be sigma-1 divided by E, whereas the strains in the direction of y and z will be minus mu sigma-1 divided by E. Similarly, the stress sigma-2 will produce strain, sigma-2 divided by E in the direction of y, whereas the strains in the direction of x and z will be minus mu sigma-2 divided by E. Also, the stress sigma-3 will produce strain, sigma-3 divided by E in the direction of z, and strain in the direction of x and y will be minus mu sigma-3 divided by E. Total strain in the direction of x, due to stresses sigma-1, sigma-2 and sigma-3 will be E1, is equal to sigma-1 divided by E, minus mu sigma-2 divided by E, minus mu sigma-3 divided by E. Similarly, E2 and E3. The stress and strain relationship for three-dimensional body. Thank you for watching.